All right, I guess we're ready to roll. So we'll get back to where we left off. And hold on one second. Oh, actually, before we do that, let's go visit Moodle. I did put some new things there yesterday. Let's see. Hold on. All right, so we now have all the notes for 3. And the problem set is there, of course. 5 is here with all the notes we've taken in the meantime. The problem set is there. The one without Bayes' theorem, by the way, because we decided not to do that because we don't have enough time. And 6 is here, which we've just started. We're about halfway through, and now there is the problem set. Now, there's a video that I want a short video that we're going to look at today. It's a very interesting application of what we're doing. It's based on a historical event. So we'll take a quick look at that today. And then if we have time, we may start chapter 7, and there's 7 and its problem set. In chapter 7, we now suddenly start to need to use either a couple of statistical tables, or else we may need to lean on our calculators for certain types of calculations, but we'll explain that as we go along. I just wanted you to see that all of this stuff is here now, and I'll just continue posting more notes as we go along. At some point, though, now, given that this is such a short class, we already have to start thinking in terms of exams. I believe, if I remember correctly, in fact, let me double check quickly with the syllabus, that we only have 2 exams when we normally have 3 during a full semester, but we don't have time to spend on a lot of exams in such a short time. So let me just open up the syllabus really fast. Here we go. That's what I thought. Okay, so it's the problem sets, the midterm, and the final. So the midterm will probably cover chapters 3, 5, 6, and possibly 7. I'll have to double check that for you. Before we have that test, we'll have a chance to practice with what I call my sample midterm, which is basically a forecast of what will come in the actual midterm. I will be posting that very soon. And one day we'll go over that in class, and then I'll post the actual midterm, and you'll have roughly a week to get it done. And the same thing with the final. We'll have a sample final where we'll get one last opportunity to review everything we did. And by the way, the final is not cumulative. It's only over the second half of the course. So whatever is not on the midterm will be on the final. So fairly soon, probably next week, we'll start thinking about working on the sample midterm, because we should be ready by then. And then like maybe a week or so later, a week and a half, we'll start working on the sample final, and then we'll be done, because this class, I believe the last day is Monday the 17th. So although we just really got started, remember, in a situation like this, every day, every class that we meet is equivalent to about 2 weeks during the normal school year. Does that sound right? Wait a minute. No, 2 days. It would be like, essentially each one of these is like a double class. Okay, so, but I mean, a class that only meets twice a week, each time we meet is equivalent to roughly, I guess, 1 week then. Well, whatever it is, it's a lot. So anyway, so we'll worry about that soon enough. But right now we want to carry on with chapter 6 and then possibly start chapter 7 today. All right. So chapter 6, we just started looking at the binomial distribution. And there's a lot of important background that we need to really understand the binomial distribution. So we were talking about arrangements and combinations so that we could fully understand the binomial formula. And so let's get back to that. Let's get this thing open. All right. So again, just a quick overview of what we've been doing in chapter 6. We introduced the concept of the random variable. and the probability distribution. And if you recall, a random variable is simply a function that assigns numbers to the outcomes of a random experiment. So in the case of our die rolling experiment, where we have a sample space consisting of EE, EO, OE, and OO, it's more convenient to work directly with numbers. So we can define a random variable X, in this case, as the number of times an even number turns up during our experiment. So for each of these elements in the sample space, we will assign with X a number that equals how many evens there are in that particular outcome. And so we set up a little chart here so you can see this. So for example, EE is assigned the value 2 because there are 2 evens here. Both of these, EO and OE, are assigned a value of 1 because there's 1 even number in each of these 2 outcomes. And then finally at the bottom here, when we have 2 odds, that means that X will assign this a value of 0 because that means there are no even numbers. So the point of X is to take these outcomes and turn them into numbers. And the reason why that's so important is because then we can calculate probabilities with formulas rather than having to count through all the different elements in the sample set. So anyway, the next step after defining X is to calculate probabilities for X. And by doing so, we are creating something that's called a probability distribution. The probability distribution takes all the values of X and assigns them probabilities. So basically, this is a 2-step process. We start by taking the outcomes of the experiment and turning them into numbers. And once we have numbers, we calculate probabilities for those numbers. Okay, so when we're done, we have a chart, here it is, which represents the probabilities of all the different possible values of X. Okay, and this little chart is a very simple example of a probability distribution. So what it's essentially saying is that here are all the different possible values of X, and here are the corresponding probabilities. But we know that these X's were generated from the dice rolling experiment. Okay, so now that when we get to this point, it no longer really matters where these X's came from. What we need to know now is what are these probabilities? So the X has basically converted the experiment into numbers so that we can calculate probabilities. Now, when we get to more advanced cases, typically we will not be using a chart. Instead, we'll be using a formula because it's just easier that way. That way we can calculate any probability that we need just by using our formula. So we introduced a couple of types of random variables. I just mentioned that a random variable X can be discrete if it only has a finite number of possible outcomes, like here. Clearly, this X is discrete because it only has 3 possible values, 0, 1, and 2. And since that's a finite number of possible outcomes, we say that X is discrete. X would be considered to be continuous if it can have an infinite number of different values. And if that's the case, we call it continuous. A good example of that would be if our X represents the time that we have to wait until the next phone call. And the reason why it's continuous is because the time itself can have a fractional component, which means that there's an infinite number of possible times that could elapse before the next phone call. And so therefore, X is continuous in this case. When we were rolling the dice, of course, there's only a finite number of outcomes that we can have. We can't have an infinite number of dice rolls, but we can have an infinite number of times until the next phone call. So X in this example is continuous. And also, we'll be looking at continuous random variables in chapter 7. For now, we're focusing our attention on discrete random variables. And so what we did here was that we introduced a couple of, well, first, before we did that, we introduced moments, which are summary measures that describe the key properties of a random variable. And these are perfectly comparable to the measures that we saw in chapter 3. For example, here we're focusing our attention on the expected value or mean, the variance, and the standard deviation. So like with samples and populations, these measures are designed to help us understand the properties of a random variable. So What's different here is the way they're calculated. Specifically, these formulas include probabilities, whereas we did not see that with samples and populations. Okay, so the expected value of a random variable is nothing more than its average or mean. But I noted here that the expected value is actually a weighted average, where we're taking each possible x and assigning it a weight, which is equal to its own probability. Okay, and then we had a formula. First, I reminded us that this example we had earlier has 3 possible values of x, and there are 3 corresponding probabilities, and they will be designated x1, 2, and 3. And the probabilities will be designated p of x1, p of x2, and p of x3. Once we have that information in place, we can apply them to this formula, where we're basically being told to take each x, multiply it by its own probability, and when we're done, add them up. And that gives us our expected value or mean for x. So remember, the notation is now very familiar to us. The only new element here is the probability. Okay, p of xi is the probability of that element or that value of x taking place. And then here we actually did the calculations. We found that in the case of the die rolling experiment, the expected number of evens is 1. So in other words, every time you roll the die twice, on average, you should expect to get a single even number. All right. Then we did the same thing with the variance. Let's skip ahead. This is the formula that we'll be using for the variance. And on the top, you can see I was showing you the equivalent version for the population. And so you can see the main difference is that with the population, instead of multiplying each term by the probability of x, we're multiplying it by 1 over the population size. So the two formulas are more similar than it might appear at first glance. But the logic is the same. We're trying to figure out how spread out the elements are in our, or the values of the random variable are, rather than elements of a population. So we did the calculations and we came up with a value of 1/2. And then we defined the standard deviation to be simply the square root of the variance. Okay. And so in this case, to calculate the standard deviation, you would simply take the square root of the variance of 1/2 and you would get approximately 0.7071. All right, then we started to introduce at least 2 very important examples of discrete probability distributions. So what that means here is that there's only a finite number of possible values that can occur. So we have the 2 binomial and Poisson, and here I'm reminding everyone that bi means 2. So that will help us understand how this binomial distribution works. Poisson, we'll see in a little bit, involves the passage of time. Okay, so they're 2 very different distributions, but they're both very, very useful in practice, which is why we will study them here. Now, the binomial distribution comes about in a very specific way. We have a random experiment with certain key properties. What are those properties? Number 1, all the trials of the experiment are independent of each other. Number 2, and this is where the name comes from, each trial can only have 2 possible outcomes, which we'll call success and failure. All right, there's only 2. And then the third requirement is that the probability of success on a single trial is a constant or never changes from one trial to the next. So if all of these 3 conditions are met, then any x that we define from this experiment, which typically is used to represent the number of successes, is considered to be a binomial random variable. And if that's the case, we can use a very special formula to calculate probabilities for x. All right, so that's why this is so important, because if these conditions are met, then we can use our formula to calculate any probability that we need for x. Now the formula is right here, and this is where we were spending most of our time last time, trying to understand what this formula actually means. So if x is binomial, we can use this formula to calculate any probability that we want. All right, so the mystery part is that piece that's surrounded by a box right there. That notation is meant to represent something very specific. And so first I showed everyone the definition in terms of factorials. So that means we now have to remind ourselves what a factorial is. It's a mathematical operator that's defined in the following way. Okay, so we recall that 0 factorial and 1 factorial both equal 1. And then after that, it gets interesting because now 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. 4 factorial is 4 times 3 times 2 times 1, or 24. And then it just keeps going on and on and on forever. So at the top, I showed another example. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, or 5,040. And I also pointed out that virtually every calculator out there does have a factorial operator button on it somewhere. In fact, if you look at your Apple iPhone, let me get this thing out for a second. If you're wondering where it is, now if you have a more advanced calculator, you should go find it on your calculator. But if you look at the scientific version of your iPhone, remember, that's the calculator, the basic calculator. Turn it sideways, and it becomes an amazing scientific calculator. The x factorial is oh man, I don't know why it's not focusing. It's in the extreme bottom left-hand corner. Okay, it's almost at the extreme bottom left. It's in the second row from the bottom on the extreme left-hand side. Okay. That's right. That's it right there. It's a little fuzzy, but I guess it's too close for this camera. But there it is. So let's say you wanted to calculate or confirm that this 7 factorial is in fact 5,040. What you would actually do is type the 7 first and then the x factorial button. And you don't need the equal signs for this one. It's just 5,040. So if you play around with it, you'll see that these numbers get very big very quickly. In fact, if you type, let me just show you another example because this might actually come up in some of these problems. Suppose you wanted to try 30 factorial. If you type 30 factorial into this calculator, you're going to get a surprise because it'll say 2.65. Let's say 25. There's a bunch of other digits as well. And then at the end, if you notice, it says E32. What that means then is that this number is so large that it had to be expressed in scientific notation. This is 2.6525 times 10 to the 32nd power. So it's an enormous number. That might be the number of molecules in the entire universe, you know, that kind of thing. It's at that level. That's how big this number is. So these can get very big in a hurry. But I just wanted to point that out so that you won't be surprised when you see this on your calculator. E32, what is that? That's a standard way of expressing 10 to that power. Now, some calculators have capital E, some of them use double E, but they all have a similar convention for scientific notation because the numbers just get too big to show in the window. That's a big number. But anyway, so what is this factorial operator for? Well, if you use it directly, you can use it to calculate the number of arrangements that can be created from a certain number of objects. Okay, so like here, for example, 7 factorial means I have 7 objects. Let's say I have 7 books on a bookshelf that just barely fits all 7 of them. That represents 5040 is the number of ways I could stack those books on my shelf, okay, from left to right. That's a lot, okay. But if you want to do an experiment, you can certainly take out some books and try, but it's 5,040. Now here I used a simple example, posters in your bedroom. Suppose you have exactly enough room on your wall for 3 posters. How many ways can you hang them? Well, each way you hang the posters is a different arrangement because all you're doing is changing the order. You're not selecting some of the posters. You're taking all three of them and changing the order. And it turns out there are 6 different ways of doing this. And we've listed them all. Every one of those choices is known as an arrangement, because again, you're just taking the same 3 objects and changing the sequence. But it turns out doing this the hard way, writing them all out, wasn't really necessary, because it turns out that the factorial operator would have told us how to do this. In this case, if you know that you have 3 posters, for example, you can easily calculate the number of ways of arranging them by calculating 3 factorial, which is 6. Okay. Now, if you have one of the more advanced calculators, I've got notes mixed in here that tell you how to find these operators on the Texas Instruments 83 and 84 series. If you happen to have those calculators, you can use these steps to calculate these values. If you have the more advanced ones, you'll have to look up the instructions in the internet, but they do have the capability of doing the same things. So 83, 84 is a very popular series. In fact, a lot of high schools require it. So you may actually have one. And if you do, this factorial operator is on the math probability menu. If you've never seen it before, it's, I don't know, let me just get mine out for a second. It's on this calculator, there's a math button in the upper left-hand corner. And when you go to the math button, if you scroll over to the right, you can see a bunch of submenus. One of them is PRB for probability. You scroll down, number 4 is the factorial operator. Okay. So right about there. I guess you can't really read it that well, but and if you have the Texas Instruments Business Analyst 2 Plus, the key you need is directly above the multiplication button. Okay, it's right there. Okay, that's the Texas Instruments BA2 Plus. Now, of course, it's backwards because I'm showing it to you in the camera. If you happen to have that calculator, the button you need is down there in the bottom. Right about there. All right, so anyway, yeah, these, you don't want to do these by hand, by the way. I mean, unless they're very small numbers. Sometimes it works to do things by hand, but often it does not, because it's just too time consuming. Very good. Now, we use this information to build up to the next step, which is what we're really interested in, is this, this thing that we were introduced to in the binomial formula, which we know is equal to n factorial over x factorial times n minus x factorial. What it represents is the number of combinations that can be formed by choosing x objects out of n. Now, the key detail here with combinations is that each choice has a unique set of letters or numbers, whatever it may be. The order in which we select these objects does not matter in any meaningful way. Okay, so as an example, we use this toppings at Haagen-Dazs. I go into Haagen-Dazs, I am allowed to choose 3 out of 5 toppings for my ice cream. There's no reason to think that the order in which I select them makes any difference. No matter how I select them, those 3 toppings will be poured on top of my ice cream, and that's what I'll be getting. So I wrote up a list of all the different ways I could choose 3 objects out of 5, and we discovered that there's 10 different choices you can have. And so the point of this is that GMC, MGC, and CMG are all the same choice. Actually, there's 6 different ways we can do this, but so I just want to make it clear, we're not counting these as separate choices, because this one represents gummy bears, marshmallows, and chocolate chips. It doesn't matter what order I put them in. So each of these is a unique combination, and we found that there are 10 of them by writing up a list. But we also want to be able to do this with our formula, because In many cases, it'll be quicker to simply use the formula than trying to simply write out all the possible combinations that we have available to us. So if you plug in these numbers, keep in mind that n is 5 because that's how many toppings we have to choose from. And then x is 3 because that's how many we're allowed to choose. And so altogether, we discovered that using the formula, we do in fact have 10 choices available to us. The order does not matter. Now, what if the order does matter? Now, by the way, as far as the binomial distribution is concerned, this is all we need. But I just want to show you that when the order does matter, then each choice has a different name. It's called a permutation. These are the ones where the order does make a difference. And since that's the case, there will always be more permutations than combinations. So we quickly summarize these three concepts. Arrangements are simply reorderings of a set of objects. Combinations are choices taken from a set where the order does not matter. Permutations are selections when the order does matter. So here's a quick example of permutations, just for your own benefit. Like I said, we don't really need this for the binomial distribution, but it's still, I want to make sure you have seen this as well, because it's important knowledge to have. Imagine the following scenario. 20 students are in a class, and they decided to start up a statistics club at Purchase College. Now, I am sure that the school has clubs. I don't know what they are, but I'm sure they have them. Every college has clubs. And the school, basically gives you rules that you have to follow. And you just have to gather people together and say, let's have a club. And then you have to fill out a bunch of paperwork and the school has to approve it. And then they have to figure out if they can give you a budget and all this and that. But suppose that this happens to be the case. Purchase says, we've never had a statistics club. Let's do it. And the students all agree. And what we're going to do now is we need, let's say, to satisfy the requirements of the school, we must have 3 officers for the club. Right. We have to have a president, we have to have a vice president, we have to have a treasurer. Now, the students are squabbling among themselves who wants to do what. They can't agree. They can't come to a conclusion. So I decide I'm going to step in and randomly pick 3 of them. And the order in which I pick their numbers, which, by the way, I'll be using numbers instead of names. I'm assigning everybody a number from 1 to 20. I'm going to randomly pick 3 numbers from 1 to 20. The first one that I pick is the president. The second one is the vice president. And the third is the treasurer. So if I choose 137, student number 1 is the president, student number 3 is the vice president, and student number 7 is the treasurer. Now, the reason why I use this example is because what if I'd chosen the same 3 numbers, but in a different sequence? Let's say, for example, I chose 713. Does that matter? Yes. And here's why. Because now all of a sudden it's student 7 who's the president. Student 1 is the vice president and student 3 is the treasurer. That's a very different outcome than this one, isn't it? So even though these can be considered the same combination, there are 2 different permutations. All right. If we were only interested in combinations, these would both be the same combination because they're the same 3 numbers. But because they're permutations, these are considered to be 2 different permutations. So there's going to be a formula here. Oh, wait a minute. Did I not? All right, let me put that in here right now. I think I might have accidentally left that out. Hold on 1 second. The number of permutations Okay, so in our case, with 20 students and 3 officers needed for the club, N is 20, and x is 3. So we'll have 20 factorial and then we'll have these two. This is the ratio that we're looking for. And hold on one second. Okay, now what I'd like to point out here, though, is that you can now go to your calculator and you can type in 20 factorial divided by 17 factorial. Now, the problem with that is that these are two gigantic, and I mean gigantic numbers. It turns out this ratio is equal to 6840. And I'll show you how I got that in a second. But there's a quicker way of doing this, or at least there's a way of avoiding these gigantic numbers. What you can do is this. 20 factorial is actually equal to, as you know, 20 times 19 times 18, 17, 16, all the way down to 1. 17 factorial is 17 times 16 times 15 times 14. So if you divide one divided by the other, look what happens. Everything cancels out. Oops. Except these three. And there's your 6840. Now, if you have one of the more advanced calculators, there will be a function in there somewhere which is labeled NPR. Okay, so on many calculators, there is a permutation button which you can use to solve directly. And while we're on the subject, there's also, in many cases, an NCR button, which is the combination button. If you have that on your calculator, you can use this directly. In other words, what you would do is you would type, for example, in the top case, you would put 20, then you would hit the NPR button, and then you would hit the 17, and it would give you 6840. With combinations, the same thing. You type the N first, the button, and then, now you notice how it says R here. We're using X. It doesn't matter. That's the number of objects you're selecting. And so this is what you would do. Oh, yes, exactly. So if you do have one of those calculators, you might as well take advantage of it. So for example, you would put 20, NPR, 17. You may not, in some calculators, you need the equal sign. Some of them you don't. And remember when we had the posters, not the posters, the toppings. For the toppings example, you would have, remember we had 5 toppings to choose from, and we were allowed to choose 3, and we ended up with 10. Okay, so if you do have those built into your calculator, now the Apple iPhone does not have permutations or combinations. It does have the factorials, but not these two. Then you just use the formulas yourself. But if you have one of the other calculators, you might as well put it to good use. On the Texas Instruments calculator, these are found in the same menu. These are on the math probability menu. Hit the math button first, go to find the probability submenu, and you'll find them right there. Okay. All right, now, here's an interesting application of this. This is something that actually happened. And so this is the video, by the way, that we're going to look at. It's kind of fun. You'll find this interesting, I think. Now, in the turn of the 20th century, the very, very famous statistician Ronald Fisher was at a party of some kind. And what happened apparently was that they were serving tea, and there was a lady at the party who had, I think what happened was she had milk in her cup, and the waiter offered to pour tea into the cup. And apparently, the long and the short of it is that this woman claimed that she could tell the difference between when tea was poured into a cup and then milk, or milk and then tea. And she wanted it one specific way. I forgot which one it was. There's one way that she preferred it. So the other people at the party were skeptical. They all said, well, how could she possibly tell the difference between tea first followed by milk, or milk first followed by tea? So Ronald Fisher, being a statistician, decided to have fun with this. He decided, why don't we conduct an experiment? So he had the waiter go back into the kitchen and pour out 8 cups of tea, where half of them had the milk poured first and half of them had the tea poured first. And then he would bring them out, and the lady would taste each one of them, and she would announce whether or not the tea was poured first or the milk. Now, just out of curiosity, how many of these do you think she got right? Just because, you know, this is something that Fisher noted and he wrote about it. What do you think? She claims that she knows how to tell the difference between the two. There are 8 cups. She, of course, didn't know which was which, and she announced after each one whether it was tea first or milk first. Well, it turned out that she got all 8 of them right. And so Ronald Fisher used what is now known as the binomial distribution to determine that the probability that she did this by pure chance, in other words, by guessing, was about 0.39%. And we're going to see later on how this was calculated, which means that the chances of her guessing are so low that he concluded that she really did know how to tell the two apart, tea first or milk first. All right, so now this video is going to be giving you the full story about what actually happened at this party. So what I'm going to do now, in the past, whenever I've shown videos in my online classes, I discovered that there can be issues with the sound. So rather than having you watch it on my screen, I'm going to send you the link through the chat room so you can watch it on your screen, so to avoid problems. Okay, oh, hold on. So I'm going to send this to you right now, and it's only a couple of minutes long. Check it out on your computer. Okay, hold on. Let me put this in the chat room. So what I'd like you to do is click that on and watch it, and then we're going to get back together and we'll see what we learned from this. All right, so check it out.
You probably know me, if you know me at all, as someone who we are in Cambridge, England, 1920. Weather could not have been more perfect for high tea on the terrace. We gathered at the table as a friendly group of colleagues. The gathering had been progressing in a lively fashion and the teacups were being refreshed when Lady Otterline abruptly stopped the server and pointed out with disdain that he had poured milk first and then tea, rather than abiding by a widely known preference for tea first and then milk. Sidelong glances were exchanged by numerous members of our assembled group as they questioned what difference could it possibly make whether milk or tea were poured first in the cup. It made, according to Lady Otterline, all the difference, a difference she could easily taste. It was at this point that I, as a scientist and amateur detective, decided to step in and proposed a little experiment. Safely away from Lady Otterline's line of vision, 8 cups of tea were prepared. 4 cups with tea poured first, and 4 with milk poured first, always in equal portions. Happily, Lady Otterline sampled each of the 8 cups and provided the crowd with her judgment of tea or milk first. Remarkably, Lady Otterline identified 8 out of 8 correctly. Could such a feat be accomplished by sheer guesswork?
Now, as I mentioned, I'm a scientist above all. As such, I left this little party with more than just some flavors. Indeed, I took with me much food for thought. Try my experiment yourself. Consider all the possible results. In what order should your cups be presented? How many cups must be correctly identified to conclude that your subject can truly tell the difference? You will undoubtedly come away with a great understanding of inferential statistics.
All right, has everyone had time to watch it? Now, when you're, Ronald Fisher was one of the great statisticians. I mean, to somebody like him, this is his idea of fun. I mean, wow, we get to do an experiment at a tea party. But that's who he was. He was that guy who's everything he thought about was statistics, statistics, statistics. And so he sees it everywhere. But of course, statistics is everywhere. It's just that not everybody notices it. But he was a pioneer. He developed a lot of the things that we talk about now originally came from him. And so what he was essentially doing was using the binomial distribution, because for each cup, either the tea was first or the milk was first. There's only 2 possibilities there. And so it was a natural extension of the binomial distribution. And so, he did think about this a lot, and he really came up with some interesting results. But it was kind of interesting how a lot of what we're seeing here was the result of a tea party where somebody says, hey, I can tell the difference between milk first and tea first. And that starts the wheel spinning. And all of a sudden he comes up with this idea. We can test whether this is true or not by doing this experiment where the teacups are randomly chosen. But he did raise some interesting questions at the end. You want to, I mean, in this case, she got all 8 of them right. What if she'd only gotten all 7 out of 8 right? Would we still conclude that she knows what she's saying? That becomes a little bit more of a gray area. So, because we'll never have absolute certainty in statistics, we have to understand how to make decisions based on data that we have, and try to understand what it means for an event to be unlikely. So here, the possibility that she guessed right 8 times it's not out of the question. It's just that it's so highly unlikely that he concluded that she knows how to tell the difference. And even though, in spite of the fact, like I said, that there's still a chance that she was just guessing. Anyway, I thought you'd find that interesting. So anyway, now we're going to look ahead, and what I'd like to do is skip over some of these. I had a couple more examples of combinations. I think we understand how that works. What I'd like to do is now jump ahead and start using this binomial formula. What we're going to do is go back to our die rolling experiment. And remember, we have only 4 outcomes. Now, by the way, let's just take a quick look at the requirements for a binomial experiment and think about our die rolling experiment. All right, so in order for an experiment to be considered a binomial experiment, we need trials to be independent of each other. So when we roll the die twice, each roll is independent of the other roll. Each die roll only has two possible outcomes because that's what we're focused on, evens and odds. And the probability of getting either an odd or an even never changes. So that die rolling experiment was actually an example of the binomial experiment, which means that we can use the binomial probability distribution to calculate any probabilities we need with this die rolling example. So in other words, instead of counting up E's and O's, we can now suddenly use the binomial distribution. All right, so here, for example, let's define X to be an even number turns up. Now, N is the number of trials, which is 2. Pi will be designated as the probability of a success, which in this case is defined as evens, and that's going to be 1/2. And that's all we need to know to calculate binomial probabilities. Okay, so let's take a look. And of course, we've already done this. We already know, for example, from before that the probability, in fact, why don't I just quickly review this chart with you? Remember before we defined a probability distribution for this experiment, and we ended up with X equals 0 has a probability of 1/4 or 0.25. 1 had a probability of 1/2 or 0.5. And 2 had a probability of 1/4. But when we did it the first time, we were simply counting up how many ways we could get this particular number of evens. And now what we're going to do is recalculate these probabilities using the binomial distribution and confirm that they're equal to each other. So here's the first case. Now remember, the formula tells us to do this. This is the lowercase x. That goes here, here, and here. Actually, this is x. This is n minus x, which is 2. Because remember, n is 2 and pi is 1/2. So what I'm basically seeing here is that I'm plugging in these numbers. N is 2, 0 is x. Now this x means I want to know the probability of getting no successes. Which means 2 odds, or OO as we called it before. This is the probability of getting OO. And so we plug in these numbers. Now, remember too that, let me see if I can find some room here. So we could actually rewrite this. Well, actually, what I did here is I actually did it separately. By plugging in these numbers, I determined that the number of ways, now keep in mind what this means is the number of combinations that can be created by choosing no objects from 2 is 1. Now that sounds like a strange idea, the idea that you're not picking anything. So what we're saying basically is that there's one way of choosing nothing. And so if you plug these into the formula, you get 1 here. The rest of it is pretty straightforward. So in other words, what you've got here is 1. Now here, 0.5 raised to the 0 power is just 1. Any number raised to the 0 power is just 1. 0.5 squared is 0.25. When you multiply these together, there you go, 0.25. So this confirmed that the probability of getting 2 odds, which is the same as saying x equals 2, is 1/4, sorry, 0. What am I saying? 0. Or 0.25. So even though we've already done this earlier with a different approach, now we can prove it with the binomial formula. Okay, so instead of counting how many ways this can happen, we end up using a formula, and we'll see that the larger the sample space is, the more convenient this formula is compared to just simply counting the number of outcomes. Now, we also want to know the probability that x equals 1. Okay, so we'll plug in the new numbers. Now, this time, the only thing that's different, n is still 2, pi is still 1/2, but this time, lowercase x is 1, because we're looking for 1 even, which is the same thing as saying either EO or OE. So we plug in the numbers. This is, of course, n, this is x, this is pi, 1 minus pi, x, n minus x. Now, on the next slide, remember, once again, what I've done is I've separately calculated this term. And let's jump ahead and look at that. And that turns out to be 2, okay? Because you have this is what you're actually getting. 2 factorial over 2 minus 1, 1 factorial times 2 minus 1, and we end up with a 2. And that basically means there are 2 ways of getting a single even number. When we plug these back in, we now have 2. And each of these is 0.5 to the first power. X to the first power is just x. And we end up with 1/2. So the probability that x equals 1, or the probability of getting EO or OE, we previously defined this or calculated this to be 1/2, and that's exactly what we're getting here. All right. And then what about 2? What's the probability of getting 2, which means the probability of getting 2 evens? Well, once again, we plug in the numbers. N is, of course, 2 again. Pi is 0.5. This time, lowercase x is 2 because we're looking for 2 evens. And on the next slide, I'll calculate this value. So therefore, 2 is okay. Just want to show you where all this came from. And that works out to be exactly 1. There's one way of getting 2 evens. Okay, now we plug that, now we're ready to plug this back into the original formula. And so we know that this is equal to 1. 0.5 squared is 0.25, 0.5 to the 0 is 1, and there you go. And so we basically use the binomial distribution to reproduce the results that we had earlier when we created this probability distribution, when we just simply counted all of the probabilities by counting how many times the E occurred in each of the outcomes. Now, you can certainly do this if you are using the Texas Instruments 83 or 84. I have the instructions here for using it to come up with all 3 of these outcomes, because that calculator actually has the binomial formula built into it. All right, it's called Binom PDF. And so here's the menus that you need to find it. And then this shows you what you enter into the calculator. So if you do have that calculator, you should look carefully through these instructions and see how it's done, because it'll certainly speed things up for you. And if you have one of the more advanced ones, it'll be in there somewhere. You just have to go find it. All right, now here's what we should do. Hold on one second. I'm going to make up a new example that we can work on together right now. And then what I'm going to do is revisit the tea lady, the teacup lady, and we're going to go back and look at our results one more time. All right, suppose that a die is rolled 3 times, and we are only interested in whether the rolls are odds or even. Now, I'm going to show you right now, the sample space for this experiment would look like this. It'll be a lot messier than what we had before. Now, once again, this qualifies as a binomial experiment, so we can use the binomial probability to calculate any number we need. And once again, let's define X to be the number of evens that turn up. So what we'd like to do is calculate, for example, what is the probability of getting 2 evens? Now, if you look at the sample space, well, all right, let me repeat it here. You could go back and use our old approach. Let me just quickly fill this in again. And you'll remember there are 8 equally likely outcomes, and 2 evens occur in these 3 cases. So we can conclude from that that the probability of X being equal to 2 and since there are 8 equally likely outcomes, each one has a probability of 1/8. So that probability would be 3/8. But what I'd like to do now is prove this with the binomial distribution. So if that's the case, then what do we need to know? All right, so if you write out all the elements in the sample space, and you find the ones that have two evens, you'll discover that there are three of them, each of which has a probability of 1/8. So therefore, the total probability must be 3/8. So we know how this is done, but now we'd like to use the binomial distribution and see how that works. All right, so if we're going to use the binomial distribution, n will be 3 because we roll the die 3 times. Each roll has a 50% chance of turning up evens. And since we're interested in 2 evens, lowercase x will be 2. So once again, a quick reminder of how this formula works. And let's see. And by the way, so 1 minus pi is a half. And because pi is a half, 1 minus pi is a half, n minus x is 1 because n is 3 and x is 2. X is 2, of course. This is pi, this is 1 minus pi, this is n, and this is x. So then we can rewrite this. Using the definition of this expression. So here we have this ratio equals 3, 0.25, 0.5. And when you multiply those out, you should get 0.375. And guess what? 0.375 is equal to 3/8. And so we just demonstrated that, why, yes, indeed, it does work. And so now I can go through and calculate the probability that x equals 0, 1, 2, and 3, and create a probability distribution for this particular experiment where I'm rolling the die 3 times and only paying attention to whether the outcomes are odds or evens. And I can continue to do this. I can roll the die 4 times and 5 and 6 and 100. I can do whatever I want. Each time, though, it'll become progressively more difficult to count the outcomes, and it makes more and more sense each time that I increase n that I use the binomial distribution. Okay, so when we have a small number of trials of our experiment, the binomial formula is important, but you can use it. You don't have to use it. But as you keep increasing the number of trials, it clearly begins to make more sense to use the binomial distribution. All right, now what about the lady in the teacups? Well, remember I said before that the chances of her getting them right by pure chance was about 0.39%. So where did that come from? Well, the way to think about it is that what is the probability of getting all 8 cups right by guessing? Well, the thing is, if you're guessing, the probability of getting a cup right would be 1/2. That's the key to the whole thing. In other words, it's 50-50. It's either tea first or milk first. So therefore, we have n equals 8 trials or cups. And pi would be 1/2. And what we're asking is the probability of getting all 8 of them right, which means x equals 8, by pure chance. All right, let me just quickly plug the formula in here. So the probability of getting all 8 of them right would be 8 factorial over 8 factorial, 8 minus 8 factorial, 0.5 to the 8th power, 0.5 to the 0 power. Now this first term is just 1. Then here we have 0.8, 0.5 to the 8th power is 0.0039. which is the same thing as 0.39%. So in other words, the chances of her doing this by pure luck or pure chance or just guessing is so remote that Ronald Fisher concluded that she must have known what she was doing, that she could really tell them apart. That's, so that was one of the key insights in all of this. There's still a chance, but it's a very trivial chance. So he concluded that she clearly knows what she's doing. Interesting. All right, now, remember a little while ago, we mentioned that each random variable has moments defined on it, just like samples and populations. And we are looking specifically at the expected value, the variance, and the standard deviation. In fact, let's go back and revisit those formulas for a second. The expected value is calculated here by multiplying each x by its own probability and adding them up. The variance looks like this. Similar to the population formula. And then, of course, the standard deviation is simply the square root of the variance. Now, when it comes to the binomial distribution, it turns out that one of the nice things about the binomial distribution is that it has its own set of shortcut formulas for calculating these moments. And when you see them, you'll say, wow, that's very simple. But they can only be used if we are following a binomial experiment. So first, let's look at the formula for the expected value of a binomial random variable. Now look how simple that is. All you have to do is multiply n times pi and you're all set. All right, so what about the variance? Surely the variance has a complicated formula. No, it doesn't. And by the way, don't forget, n is the number of trials and pi is the probability of success on a single trial. Here's the variance. Look, it's almost the same, except we've multiplied at the end by 1 minus pi. And of course, you know that the standard deviation must therefore be the square root of this variance. Yes, exactly. Now, if you remember from the die rolling experiment, we previously determined that the expected value was 1 rather, When we roll the die twice, the expected value is 1, the variance was a half, and standard deviation was about 7071. So what we're going to do now is confirm these with the binomial shortcut formulas. Here we use the full version of those formulas. Now we're going to use the shortcuts. So if you recall, for this die rolling experiment, there were 2 trials, and the probability of getting an even number is a half. So look at this, expected value is 1. Look how easy that is. Multiply them together and you're all set. Look at the variance. Remember how much work that was? Wow. Just multiply n pi 1 minus pi and you get your answer of 1/2. It's so much simpler. But of course, before we didn't know that this was a binomial experiment, and therefore we could use shortcut formulas. We used the general formulas, but we've proven that they worked in this particular case. And now, of course, the standard deviation must be the square root of that. That never changes. All right. Wow, boy, the time flew sometimes the time goes very, very quickly. All of a sudden, I just noticed it's time for our little break. So we'll stop right here. We've got one more thing to consider with the binomial distribution, and then we can dive into the Poisson distribution. Okay, so when we get back at around 11:30, we'll pick it up by showing you basically a graphical illustration of the properties of the binomial distribution, and then we can introduce ourselves to the Poisson distribution. All right, so see you all in a bit. All right then. All right, so here's what we're going to do. Just to wrap this topic up, we're going to see a series of histograms that help us take a close look at the properties of the binomial distribution. So we've already been introduced to histograms. A histogram is a series of bars that represent some type of probability distribution, where each bar represents a single value or range of values, and the height of each bar represents a probability. So what we're going to do here is assume that we're conducting an experiment. Let's say we're flipping a coin, and we're flipping the coin 10 times. And let's say X represents heads. So if we flip the coin 10 times and X represents, or actually, no, it can't be heads. I just realized it has to be something different because the probabilities are all going to change. So let's just say that this is some binomial experiment where we have 10 trials, and X is simply the number of successes, however they're defined. Because we need to do this 3 different times, one for each of 3 different probabilities. So in other words, we'll start out with a case where there are n or 10 trials. The probability of success is 0.2. Now, if we do that, the resulting histogram looks like this. So what are we trying to see here? Well, first of all, if you notice, when we have 10 trials, the outcomes are limited to 0 to 10, right? So we have 1 bar for each of these 10, or actually 11 different possible outcomes. And the heights of these bars represent probabilities. So when pi equals 0.2, the most likely outcome is 2 successes out of 10 trials. And then there's a very high chance of getting 1 and a slightly lower chance of getting 3. And then after that, the probabilities fall off quite quickly. And in fact, down here, the bars are so short, you really can't even see them. They're not 0, but they're very close. So you might recall that earlier on, we described this type of distribution as being skewed to the right, or positively skewed. Now, if we switch that probability to 0.5, let's see what happens now. Aha, now that changes everything, doesn't it? Because now the most common outcome is the 5. But if you notice, the 4 and the 6 are equally likely. The 3 and the 7 are equally likely. The 2 and the 8 are equally likely. The 1 and the 9. So what we have here is symmetry. The left and the right of 5, that is. Everything to the right of 5, everything to the left of 5 are mirror images of each other. And so the last case is one where pi is 0.7, and you can probably guess it's the opposite of this one. And that's absolutely correct. You can see here that the most common outcome is 7, followed closely by 8 and 6. Then after that, the probabilities fall off very quickly. And down here, we have these very small probabilities, which you can just barely see. And you can call this one negatively skewed. So each binomial, and by the way, for the binomial distribution, there's an infinite number of possible combinations of n and pi, which means there's actually an infinite number of binomial distributions. And so you can see these are just 3 of them. And you can tell by looking at these histograms a lot about the distribution because of the basic shape of these bars and the way they're distributed. So histograms are often a good way of taking a look at data and gaining insights into how it is distributed. And so this proves to be a very useful tool for analyzing data. All right, well, anyway, so now we can move on to the Poisson distribution. The Poisson distribution is another discrete distribution, but what's different now is that instead of thinking in terms of a series of trials, like flipping a coin or rolling a die, instead, we're observing the passage of time, and we're observing how many events occur during that passage of time. So we're trying to measure the probability that a given number of events occur during a specific time interval. You might, for example, want to know what is the probability that over the coming year we'll have, or how many times over the coming year we'll have more than 2 inches of rain, let's say, or 3 inches of snow, or something along those lines. So we're thinking in terms of time now. Now, like with the binomial distribution, there's a formula that we can use to calculate probabilities when we have, when our situation involves time rather than trials. Okay, so here's what it looks like. Now, there's some interesting new items in here that we haven't really seen before. Well, we know what this is. This is, of course, x factorial. X is the number of events that occur lowercase, that is. Capital X is the Poisson random variable. Now, here's something new. This is a new Greek letter that we may not have encountered before. This is the Greek letter lambda. And in this situation, lambda represents the average, number of events that occur per unit of time. Now, by the way, the time frame is defined in the problem. It could, for example, be that the time frame is a year. It could be a week. It could be a day. It could be an hour. It could be anything. That's something that you have to be told in the problem. So lambda represents the average number of events that occur during that particular time frame. And then finally, here's something you might not have seen before. This E is actually a constant. It's approximately equal to 2.71828, and it goes on and on and on forever. Your calculator will most likely have a button labeled e to the x power. If you ask it to show you e to the first power, it will show you this number, about 2.71828. It shows up a lot in financial applications. You might not think it's that important, but it really is, surprisingly enough, very important. And so in a lot of ways, it's like pi. Pi is approximately 3.141, et cetera, et cetera. Very strange number, but it shows up a lot in trigonometry, as you know. E shows up a lot in other types of applications, including finance. So it's a very important number. Anyway, so that's our basic formula for calculating Poisson probabilities. But of course, we have to make sure that we're using it when it's appropriate. So if the situation involves observing events occurring during the passage of time, then we can feel free to use the Poisson distribution. All right. And by the way, if you have the Texas Instruments 83 and 84 series, there is a Poisson function in there. There's also an e to the x function, and the instructions are here for finding it. But right now, let's just take a quick example of how this Poisson distribution works. Suppose that we note from experience that on average, a person receives one message on his cell phone every hour. Okay, so one message per hour. Already we know that we're dealing with the Poisson distribution. We also further know that lambda equals 1 because we're told that the average number per hour is 1. So already we have that information. Then we're being asked to calculate what is the probability of getting 2 messages in the next hour. So that lowercase x is 2 because that's what we're trying to find out. What's the likelihood of getting 2 when we normally average only 1? So we're going to use the Poisson distribution to calculate this. And it's a fairly straightforward formula. It's not quite as time consuming as the binomial distribution. But, you know, like all others, it takes a little practice. So remember, lambda equals 1, lowercase x equals 2. So e to the minus lambda, lambda to the x, x factorial, we plug in the numbers. Here's our lambda. And well, it's getting a little messy here, but you can see we're just plugging everything in. So now, of course, let me bring this down here for a second. One squared is just 1. 2 factorial is just 2. So what we're essentially doing here is multiplying e to the minus 1 by a half. Now, if you go to your calculator, you'll see that e to the minus 1 is approximately equal to 0.3679, approximately. So 1/2 of that turns out to be about 0.1839. So there's roughly an 18.4% chance that in the next hour, this person will get 2 messages on their phone instead of the usual 1. And that's all there really is to it. It's not maybe quite as involved as the binomial distribution, but we just have to make sure that we use it when it's appropriate. Now, again, if you do have the Texas Instruments series, I have the instructions here for using them to calculate these directly because the Poisson probability distribution is in fact built into that calculator. If you don't have it, that's fine. You can do it the way we just did it. Okay. Now, actually, just to get a little more practice, why don't we try this? Based on the previous example, what is the probability of getting 3 phone calls during the next hour? So remember, the formula is this. And we already know that lambda is 1, and now this time x is 3. Okay, so we plug everything in. E to the minus lambda is e to the minus 1. Lambda is 1. We raise that to the 3rd power. And we divide that by 3 factorial, which is, of course, 6. So you actually end up with e to the minus 1 times 1 over 6. And that works out to be about 0.0613. All right, and that's all there is to it. Now, remember before, we did mention that when it comes to the moments of a random variable, there were special shortcut formulas for the Poisson, the binomial distribution. Let's go back and revisit that for a second. So originally, when we introduced the moments, we had 3 fairly complicated formulas, which work for all discrete random variables. And so these formulas always work. But sometimes we don't need them because there are alternative shortcuts. So we saw already that with the binomial distribution, the shortcuts are pretty short. Let's see, let me go find them again. Oh God, where are they? All right, I'll tell you what. There we go. All right. So the formulas for the binomial, the expected value was simply n times pi. The variance was n times pi times 1 minus pi. And the standard deviation was this. Now, the same thing holds for the Poisson distribution. It has its own unique set of shortcut formulas for these moments. So let me show them to you. In fact, if anything, they're even shorter than the ones for the binomial distribution. So look how easy they are. The expected value equals lambda, the variance equals lambda, and the standard deviation equals the square root of lambda. It's that simple. Look at that. It's amazingly simple to calculate moments with the Poisson distribution. I don't think any of them are any simpler than this. This is as simple as it gets. All right. Now, based on our cell phone example, remember we were told that lambda equals 1. So the moments are easy. Look how easy this is. And in fact, just by an interesting coincidence, they're all equal to 1. Okay, on average, we get 1 phone call an hour. The variance is 1, and the standard deviation is 1. You don't see this very often. All right, now, just like before, a few minutes ago, we were looking at histograms to help explain or understand the properties of the binomial distribution. We're going to do something similar right now with a Poisson distribution. This time, we're going to change the value of lambda. Okay, so we're going to look at 3 cases. The first one will be where lambda equals 1. The second will be where lambda equals 2. And the third case where lambda equals 5. Okay, so let's start with 1. Now, we just got through doing these 2 probabilities. Okay, about 18 point something and about 6%. What you notice here, interestingly enough, is that these first 2 are the same. You do run into that sometimes with the Poisson, which you don't usually get with other distributions. So you can see that the most common outcomes are here, and then it falls off very, very quickly. So it's not exactly negatively skewed. It is and it isn't. I mean, it doesn't fall off. And also, by the way, don't forget with these 2 specific cases, we can't go below 0. This is one way. The one thing we need to pay attention to with Poisson and binomial, if you notice, we never have a value less than 0. But if you notice with binomial, you notice how the probabilities start out very low and then they go up and then they peak out and then they fall back down again. With Poisson, it doesn't always work that way. So if you notice here, it starts very high and then it just simply drops off. With lambda equals 2, it looks a little bit more like binomial because it rises, reaches a peak, and then it falls off again. And this time, the 2 values that are equal to each other are 1 and 2. So what this really means is that when you get good at this, you should be able to tell at a glance whether this distribution is Poisson or binomial. They each have their own unique features, and you can see this is one of the bizarre things about the Poisson is that you typically have these 2 bars of the same height, which you're not getting with a binomial. All right, here you don't see any of these bars of the same height. It's very unusual. Whereas it happens all the time. I mean, except on either side, but I mean not right next to each other. Whereas here it happens all the time. And then in the case of 5, it's getting very close to being symmetrical. Again, you get those 2 in the middle that are exactly the same. And that's one of the ways we can sort of tell that this must be the Poisson distribution. So now when does this really come in handy? Imagine you have a set of data and you're not sure what distribution it follows. In these cases, we've been assuming that we knew what distribution our data followed. it's not always that simple in the real world. We often have data where it's not clear what distribution it follows. And one way we can try to figure it out is by looking at these histograms, because they can give us a lot of insights into how the data are actually distributed. So if we're not sure, then we can lean on these graphs to help us determine what distribution this is likely to be. So that's one way in which this can be very, very helpful. It's not just because the pictures look so nice, although they certainly do, but you know, that's really one of the main benefits of this, is that it can help us identify the properties of a particular set of data. All right, now let me save this for a second. Today's the 28th. So I think we do have time to at least take a peek at chapter 7. By the way, I think what we should probably do, what's going on here? Oh, it's just taking its sweet time. It's a very large file. You know what, why don't we do this? I think what we should do is have the chapter 5 problem set due by next week. But again, because there's a holiday coming up, why don't we have it due next Tuesday? So let me just throw that in here before we completely forget. So the chapter 5 problem set is due on Tuesday. Oh, what day would be next Tuesday? It looks like next Tuesday is the 4th. Okay. Okay, I think that'll do. And then of course we'll get to 6 and 7 and all the rest, but that'll do for now. Okay, so all right, so let's at least take a peek at 7. Now 7 is a different type of probability distribution that we'll be looking at, because we're going to be for the first time considering what are called continuous distributions, which means they allow for an infinite number of possibilities. And furthermore, they allow for negative numbers. With Poisson and binomial, we did not have any negatives because of the way they were defined. Like if you're rolling a dice 5 times, you can't have a negative number of heads or tails, for example, or sorry, evens or odds. With Poisson, if we know that there's so many phone calls taking place every hour, we can't have a negative number of phone calls. But when we start looking at continuous distributions, suddenly we have to allow for the possibility of negative values on top of the idea that we have an infinite number of possibilities. Now, because of that, the calculations get even messier, and we're going to have to lean on another way of doing the calculations. We can either use calculators or else we can use tables. Okay, so we'll explain that as we go along, because unlike the binomial and Poisson, where it's not hard to calculate them, it's easy to plug the numbers in. With the continuous distributions, it's much, much messier. So we'll rely on something else, which will either be tables, like I said, or calculators. But anyway, what's going on in this chapter is that we're introducing a very important probability distribution, which is continuous. And that's because it allows for the possibility of an infinite number of values, because the values can be fractional or have a fractional component. They're not restricted to integers like they were in chapter 6. All right, so if I roll a die 5 times, I can't ask a question like, what's the probability of getting 3.7 heads or evens, because there is no such thing. But here, anything is possible. So remember, continuous means infinitely many possibilities, like the length of time until the next phone call. Anytime time is involved, whatever variable we're looking at is going to be continuous, because the number of possible times is infinite. Even though we don't have negative times, the number of possibilities is still infinite. In fact, you might recall from some math class you've had along the way, if you look at the real number line, the number of values between any two integers, let's say 1 and 2, is infinite. There's infinitely many values between any two integers. So even if our variable was restricted to being between 1 and 2, as long as we allow for fractional components, then we will have an infinite number of values. All right, well, anyway, now what's going on here? Now there's some new terms that we need to introduce here. The function that lets us calculate probabilities has a very formal name. You don't have to memorize this, but the formula now in this chapter is called a probability density function, which is often abbreviated PDF. And what's changing now is that instead of having a series of bars like we did in chapter 6, like here, for example, this is a classic example of a discrete distribution, which is illustrated with a histogram. What's happening now is that if we were to try to draw this graph for a continuous distribution, we would have an infinite number of bars. And so in order to avoid dealing with an infinite number of bars, we're going to think in terms of not the actual heights of the bars, but the area of the bars. In other words, we're going to connect all these bars with a curve. And then the areas between different points will be used to calculate probabilities. So for example, for any continuous distribution, the total area under this curve is defined to equal 1. So if I want to know the probability, let's say being between 2 and 3 here, what I'm actually doing is calculating the area. Let's say the area is 0.7. Therefore, the probability of being between these 2 points is 0.7. So in other words, now we're thinking not in terms of the heights of the bars, but the areas under this curve that are formed by the tops of the infinite number of bars. So it's an area now rather than the heights of individual bars. And that has some interesting consequences, a lot of very interesting consequences as a result of this. And by the way, this is one of the reasons why we have to lean on tables now or calculators, because calculating the area under that curve would be extremely messy to do it with a formula. Very, very messy. So instead, we have tables that have been set up for us to calculate these probabilities. Now, one of the interesting results of this, the idea of the continuous distribution, is that because there's an infinite number of possibilities, the probability of a single value is defined to be equal to 0. So for example, we know that if X is the time until the next phone call, it has an infinite number of possible values. The probability that the time until the next phone call, therefore, of it being precisely 1 minute, will be considered to be 0. Instead, what we might do is say, well, what's the probability that the next phone call arrives, let's say, between 1 minute and 1.1 minutes? That we can do. But the probability of it being precisely 1 minute is going to be considered to be 0. Because it's 1 out of an infinite number of possible values. So therefore, for precisely 1 minute, we'll define that probability as 0, but there's nothing to stop us then from asking the question, what's the likelihood that the time until the next phone call is somewhere between 1 and 1.1 minutes? Now I see on the next slide, I have an example of, well, I changed it to 0.9 and 1.1 minutes, but you get the idea. And so let's say instead we're interested in the probability that the phone call arrives within between 0.9 and 1.1 minutes. How do we figure that out? Well, if you look at the curve here, we're looking for the area between 0.9 and 1.1, and that's going to be our probability. So again, we're focused on areas now. And just in the general, most general terms, the probability that x falls between y and little x is the area under that curve between those 2 points. Now, here's another one of the wacky consequences of this. It turns out that with a continuous distribution, we have some very oddball results here. The probability that x is less than or equal to some constant lowercase x is the same as x being strictly less than x, and vice versa. So unlike chapter 6, where that makes a big difference, here we don't have to make a distinction between less than or equal to and strictly less than, or greater than or equal to and strictly greater than, because they both ultimately mean the same thing. And that's something that takes a little getting used to. Now, let me show you why. You're probably wondering why. How is this possible? Well, remember, we did say that with a continuous distribution, the probability of equaling a specific value is 0. So watch this. So I think you'll all agree the probability that x is strictly, or sorry, less than or equal to lowercase x is the sum of the probability of x being strictly less than x and the probability that x exactly equals x. And so with a continuous distribution, we've already seen that this probability equals 0. And that's the reason. So they mean the same thing when we're dealing with a continuous distribution only. With a discrete distribution, no, it makes a big difference which one you're talking about. But here, it does not. Okay. So now, of course, the greater than situation is exactly the same. So and then with a continuous distribution, we know that this probability is 0, so therefore okay, and so they're now the same. All right, anyway, so now let's introduce, now we're only going to look at one continuous probability distribution. This one is by far the most important, really, of all the distributions, not just continuous, but probably discrete as well. In other words, if you use enough statistics, you'll find that you're mainly using this distribution, which is the so-called normal distribution. It's going to show up in a lot of different applications. And in fact, it's going to continue to show up throughout the rest of the chapters in our course because it's so important. So this is really by far the most important of them all because it shows up in a lot of applications. It is very useful for describing what happens in the real world. So many, many results are derived with this normal distribution. It is a continuous distribution and it has some very interesting properties. First of all, when you draw this thing, you can see it is often described as a bell-shaped curve. That's pretty much what it looks like. But unlike the Poisson and the binomial, which we've already seen their histograms, here remember, because this is a continuous distribution, we're not looking at bars any longer, we're looking at curves. And what you'll notice is that, first of all, in the center, we find the mean. Now, here's our old friend, the Greek letter mu. Once again, we're using it for double duty. We used it as the mean of a population, but here we're going to use it as the mean of a probability distribution. And number two, our old friend sigma, which we've previously seen used as the standard deviation of a population. Now it's being used as the standard deviation of a probability distribution. So don't get confused, but it should be clear from the context which one we're talking about. So the mean is in the center. And if you notice, the right-hand side of this curve and the left are identical to each other, which means that this distribution is symmetrical about the mean. We have that wonderful property of symmetry, which you'll see later on will help us with our calculations in many cases. And like all other continuous distributions, the entire area under that curve is defined to equal 1, so that areas correspond to probabilities. And if you notice, the curve goes all the way out on the upside to positive infinity, and on the downside, it goes all the way down to negative infinity. So the curve covers the entire real number line, but the area shrinks to almost nothing very, very quickly. So in other words, it might sound like, well, how can that be? Because the area shrinks up very, very quickly as we go up to positive infinity and down to negative infinity. So we're going to use this curve to calculate probabilities by looking at areas under the curve. Now, I'm going to show you the formula that is associated with this distribution. That curve is basically a graph of the probability formula that goes with the normal distribution. Now, it's going to be even messier than what you saw with the Poisson and the binomial, but fortunately, we're not actually going to use it to do our calculations because that would get us involved with calculus, which we're not going to do here. Instead, I just wanted you to see what it looks like. And the important detail here is that it contains a lot of elements that we're already very familiar with. Pi, by the way, this pi is the actual pi that you know from high school, 3.141, not the pi that we use in the binomial distribution. Sigma is our standard deviation, of course. Mu is the mean. E is this 2.71828 that we just encountered previously. And by convention, instead of calling this P of X, we call it F of X. And that is there to remind us that this is a continuous distribution. So this is what's actually going on behind the scenes of that bell-shaped curve. This is a graph. The bell-shaped curve is a graph of this function. Now, you may remember I mentioned that there's actually an infinite number of both binomial and Poisson distributions. The binomial distribution is characterized by the values of n and pi. The Poisson is characterized by lambda. The normal distribution is characterized by these two values, mu and sigma. So what that means is that they're graphs depend on those values. And I've got some examples coming up. First of all, we've already seen that the curve is symmetrical. And that's the reason why the sigma is here. This tells me that sigma determines how spread out the distribution is. Okay. So now what I want you to see is the relationships between normal distributions with different values for mu and sigma. So here, for example, we've got two different normal distributions. And if you notice, they both have the same standard deviation, which means that they're the same shape. The difference between the two is that the mean is 10 in the second case, and the mean is only 0 in the first case. So you're basically taking a copy of the first distribution and moving it to the right by 10 units. I mean, to the best of my ability to draw them, they're supposed to be identical to each other, except that the one on the right has a higher mean than the one on the left. Okay, so what this is telling us is that the mean determines the location of the normal distribution. On the real number line. Okay. Now over here on the next graph, we're going to see the opposite. We'll have two curves with the same mean, but two different standard deviations. Okay, and so you see what's different now. They're in the same location, but the first curve, the tall one, has a very small standard deviation, and the very flat one has a very high standard deviation. So what this means is that sigma determines the spread of the distribution. Okay, so the mean determines the location, the sigma or standard deviation represents the spread. And there's an infinite number of other possibilities. I just wanted you to see how they compare with each other when they have either two different means or two different standard deviations. All right, now it turns out that yes, there's an infinite number of distributions, but there's one that we see most often and it is most useful. And that is the case of the so-called standard normal distribution. All right, and so what separates it from all the rest of them is that it is so useful that the tables that we'll be using are based on this so-called standard normal distribution. Okay, so what is so special about this standard normal distribution? Okay, well, what we have is a mean of 0 and a standard deviation of 1. Now, you might not think that's such a big deal, but it makes it easier to interpret our results. This is really one of the reasons why it's so popular. And so it's so important that it's given its own separate name. The others don't have their own names. This one does. So this is the one that we'll see used in normal tables, and it will enable us to calculate something that we will call z-scores, which you'll see are very useful in practice. So this is the most important of all the normal distributions by a long shot. Okay, Now, one more thing. Up to this point, we've been using the letter X to represent random variables. Just, remember for Poisson and for binomial. Here, we're going to make a slight change. From now on, X will be used to represent any random variable except when it comes time to the standard normal, we're going to replace the X with a Z. This is by convention. The Z is understood to represent the standard normal distribution. All the rest are going to be represented with X. Okay, so that shows you how important this is when it gets its own letter. So anyway, I have done some graphs in Excel. It's a little easier sometimes. So here's one of them. Excel sometimes does a good job with graphs. Sometimes it doesn't. But because it's the standard normal, we're going to use the letter Z, and the center or mean is 0, as you can see right there. It goes out into the tails. It goes out forever. But for all practical purposes, if you notice this -3 here and this +3, the area direct below here and above here are less than 1% of the total. So the vast majority of this distribution is in this range right here. The rest, all of it together, adds up to less than 1%. It's very, very, very small. All right, now, what I'd like you to do is see how those numbers connect to the standard normal distribution. If you notice here, I've got the same numbers, but directly below them, what you're seeing is that 0 is the mean. A 1 actually means 1 standard deviation above the mean. -1 can be interpreted as 1 standard deviation below the mean. And similarly with 2 standard deviations above and below the mean, and 3 above and below the mean. So these numbers actually are directly tied to the number of standard deviations above and below the mean. Now, one of the properties of the normal distribution is that roughly 2/3 of the area is in between plus and -1, or within 1 standard deviation of the mean. Okay. Now let's stretch it out to within 2 standard deviations of the mean. And you'll see that that grows very quickly. It covers almost roughly 95% of the entire distribution is within 2 standard deviations of the mean. Okay, so let me quickly show you that. And that's, again, one of the properties that's based on the way the curve is defined. About 95.44% of the area is between those 2 points. So for a variable, let's say that we're looking at rainfall. And let's say that, just to mention this on the side, just as a quick example of what this is all about. Suppose we discover the mean rainfall is 40 inches per year, and that the standard deviation is 5 inches per year. This means that 95.44% of the time, rainfall will be between 2 standard deviations below the mean, which is 30, and 2 standard deviations above the mean, which is 50 rather. Okay, because we're assuming that the rainfall is normal, Well, actually, let me include that in here, normal. So, all right, hold on. So suppose that rainfall is normally distributed with a mean of 40 and a standard deviation of 5 inches per year. So just from that alone, we know that about 95.44% of the time, the rainfall will be between 30 and 50 inches because it follows the normal distribution. So in fact, I might as well keep this in the slides. It's a good example. I like it. I just want to change the font. I think it's Arial that we're using here. Yeah. All right. Okay. So, and then for 3, if you go all the way out to plus or minus 3 standard deviations, you're covering 99.7% of the distribution. So all the rest is only about 0.3%. Okay, now, this is fine as far as it goes, but for most cases, we'll need to calculate a very different set of probabilities that are not listed here. So what we need to do is learn how to use these tables, which I posted on Moodle, by the way. And we'll be using them a lot tomorrow. Not today, it's too late, but here they are. Like, let me just open one of them up at random. There's 2 of them, one for positives and one for negatives. And it's just a whole table of values. And we'll use this table to come up with probabilities for different scenarios. Okay. Actually, I should have deleted that, but yes. This is what we'll be using extensively tomorrow to calculate probabilities so that when we're done, we can calculate any probability that we need, not just these. These are very important cases, but this just covers, this is at the tip of the iceberg. We have to be able to calculate any probability that we might encounter in the real world. And we'll do exactly that tomorrow, starting with these normal tables. And then I'll show you, if you have the right calculator, you can also do this directly on your calculator. I do have the instructions in here for the TI 83 and 84, but you don't need them. You can use the tables. Either way, you'll get the answers. Okay, so I think that's where we should leave it off here. We don't want to start this now. It's too complicated to start with 4 minutes left and then pick it up tomorrow. So instead, we'll stop right here and we'll just carry on. And then, and don't forget that starting with the chapter 5 problem set, you can start working on it now if you want to, but it's not due until next Tuesday. Other than that, I think we're all set. Okay, so does anybody have any last minute questions?
Yeah, just had a quick question about the problem, the chapter 3 problem set.
Yeah.
So it's fine to submit that by email.
Oh, is there a problem with it?
Oh no, I just wanted to check it, like, to make sure there wasn't a place on Moodle we should be submitting.
No, you know what? I'll tell you what. I am so bad with technology. I mean, it's possible that it could have been set up that way, but you know what? I don't know how to do it. And the people who do are probably not in their offices right now anyway. So I thought, you know what? I think you can just email it to me. Maybe in the future, I'll investigate how to set up a Dropbox here for homeworks, which probably would be very convenient, but it's not there right now. It's not, let's just say it's not obvious how to do this. And therefore it is, you'll have to use the old fashioned approach. Just email it to me. Now, you probably should try to send it to my Purses account, but if you forget and send it to my Gmail account, it's okay. I'll see it.
Okay, and that's by midnight tonight.
And it's what?
And that's by midnight tonight.
Yeah, you should have it ready by midnight tonight.
Okay, great. Thank you.
Okay, Haley.
Yeah, hi. Sorry. I just wanted to let you know, I emailed you twice because I accidentally submitted my problem set with one question that I didn't answer correctly, and then I went back
Oh.
and redid it.
All
So
right.
the second email says like correct, just to let
Oh,
you
all
know.
right. I'll look out for that. And if I overlook it, you can remind me. I'll try to correct the new one.
Oh, cool. Thank you so much.
Okay.
Appreciate it. Sorry about that.
Sure, no problem. Yeah, there
Thanks.
shouldn't be a penalty for sending it in early. You know what I mean? Like otherwise you send it in and you're committed. No, it's fine. I'll look at the new one.
Oh, cool. Thank you so much.
Okay.
Thank you.
Now we have
All right.
Zoya.
How do I get out of here?
Oh, the sound is really bad.
Is this any better?
That's better, much better.
Okay, sorry, thanks. Just confirming your purchase email is aanderson@purchase.edu?
No, I think it's, oh my God, I don't send things to myself. I thought it was Alan Anderson at,
Okay, I haven't gotten an email from you aside from the Gmail account, so I just wanted to confirm
all
your
right,
purchase.
I will double check it
Alan.
right now by sending myself a
Thank you.
test message.
Thanks so much.
Oh, sure. I'm pretty sure that's what it is.
And then just wondering if you had a few minutes after class to go over just one question on the
Sure.
problem
Yeah.
3 homework set. Thank you so
Okay,
much.
so let me do that right now. Yeah, it's my full name.
Great, I see it now. Okay.
Well, yeah, there it is. It went right through. Okay, great. All right, anybody else? All right, well, I guess we're done then, and we'll stay here. Zoya wants to ask me about chapter 3 problem set, so we're going to do that now. You can stay and watch if you want to. Let me just get it open. Yeah, this is not proprietary at all. All right, so what would you like to go over?
So I had to find time with the homework assignment. It was just for problem 3A. I'm having trouble. I keep second guessing how to set up the formula for 3A.
Yes, it's a weighted average problem.
Okay.
And so what you have to do is go to that. Let's go to the chapter. It's just like the one with the lottery.
Okay.
So in other words, you've got, let's see, where is it? So what's happening here is that the weights are 20 for the 1% loss, 30 for the 0% loss, 30 for the 1% gain, and 20 for the 2% gain. And the percentages are the X's.
Right.
So you can make up a little list here of the weights, and the X's would be the percentages, like -1%, 0, 2%, that kind of thing. And then you just plug them into this formula where you're just multiplying in the numerator each weight by X, adding them up, and the denominator you add up the weights, which in this case adds up to 100 because there's 100 observations.
Gotcha. So the percentages are the X's and
Yes.
the number of times are the weights.
Those are the weights, right? And so if you plug those all in, you shouldn't have any trouble with it.
Okay, great. Thank you so much.
Okay, you're welcome.
Thanks.
All right, is anyone else still hanging around there? Anyone else want to ask any questions? All right.
Yeah, I had a quick question.
Oh, yeah, go
Sorry.
ahead.
But this one's pertaining to homework number 5.
Oh, all right, let me go get it. Let's see now. Oops, I think I opened the wrong thing, sorry. Here we go. Yes, here it is.
Okay, so I'm at F on the first question. And so I was looking at it, and that's like an intersect question.
It
correct?
is,
Like,
right.
okay, so when I was looking at it, I kind of wrote out the sample space and sample
Good.
points.
Good.
There's no actual ones that intersect on
That's
that.
right. So
that
that means,
correct?
that's correct. That means the intersection is the empty set.
Okay, so it's actually it's just like I put brackets, just the
That's
open
right. Just two brackets
with nothing.
in
Okay,
between. That's correct.
Got it.
And
All
the
right.
probability, by the way, the probability of that is zero then.
it's 0.
Right. In other words,
Alright,
the
cool.
intersection is the empty set, but the probability is 0 because that means that this event can't happen.
Right. Okay. Perfect. That's what I was thinking
Oh,
because
okay.
I did want what is that? That's D and E, and then I got to that one,
Right.
and then obviously F comes to the next one, and I'm like,
Yeah, no,
I
that's.
thought it was right, but I wanted to make sure. Cool,
Okay,
perfect.
no,
Thank you
that's
so
right.
much.
You're welcome. Okay. Anyone else? All right, then. I'll see you all tomorrow at the usual time and place.
Thank you, bye.
Okay, bye, everyone.